The broadcast is now starting. All attendees are in listen-only mode.
Hello. Welcome to today's IChemE Safety Centre webinar. My name is Trish Kerrin and I'm the Director of the IChemE Safety Centre. Joining us today we have Garry Law, who will be taking us through his presentation Over the Top, Process Safety Lessons Related to Liquid Levels in Process Vessels and Tanks. So this is a very important topic and one that tragically so often goes wrong, as we see. So Garry is a professional process safety engineer and he is a consultant with technical safety consultants at the moment. He also does some work with Safety Solutions and with IChemE as one of our trainers. And I've known Garry now for a number of years and I'm really looking forward to his presentation. So before we get going with the presentation, if you have any issues connecting in, then please feel free to send me a message in the chat box and I'll try and resolve whatever the connectivity issues are that you're having. If you have any questions as Garry goes through his presentation, please put them in the questions box on your screen and we will answer them at the end of the presentation. So I'll be reading them out to Garry and he'll answer them at that time. So we will be taking questions at the end, but if you think of them as we go through, please start to put them in to the questions box. So without further ado, I will now hand over to Garry and he will commence his presentation. Welcome, Garry.
Thank you, Trish. Hello everyone around the world in Australia. Thanks to Trish and the IChemE Safety Centre for inviting me to speak today. I know we did this talk a few months ago to one of the local branches here in Australia, and so it's great to sort of open up now to a wider community and get the messages out to the very important messages, as Trish said, on the tank level and vessel overflows. So I hope everyone's doing okay in lockdown. We've just about come out of ours, but never say never. We tread carefully and hope everyone's safe and well out there. So just a bit of, before I go into the background of the presentation and myself, so just to say, sort of process safety, very important. It's a bit more of a job, more than a job for me. It's more of a passion. So I get a lot out of the teaching and sort of giving back through the training that IChemE and others provide in the industry. And so, yeah, it's a great pleasure to sort of provide all these lessons that I've sort of built up over the last 25 years or so. And hopefully others won't repeat the same instance again. And hopefully you can pick a few of the gold nuggets out of my talk and take those away to act on after today. So the agenda for today, just an introduction about why are we talking about overfilling again? Why is level measurement an issue? So we'll talk through those things at the start. And also quite a bit about human factors in relation to the knowledge of engineers and operators, as well as operator error. Picking up on a few well-known international examples, Buncefield and Texas City are well-known within the hydrocarbon industry, and hopefully outside of that by now as well. Both of those happened in 2005, and we'll also talk about another incident that happened just a few years after that, which was very similar to Buncefield. We've got something like 6 additional case studies that sort of built up from sort of my colleagues and my own examples over time. Most of those are actually to do with process vessels rather than tanks, although we do go back to tanks towards the end. I also talk a little bit about the links back to how you identify these issues during process hazard analysis or identification studies, such as HAZOP, hazard, etc. And also some of the risk assessments you might do on levels, particularly instrumented systems with SIL or safety integrity levels, and layer protection analysis. And then we'll just wrap up at the end and then come back for some questions. So yeah, like Trish says, just put your questions in the chat box and I'll try and answer as many of those as I can at the end. So a bit of background to myself. So I started out on an oil refinery in the UK, Humber Refinery, and that was when Texas City incident happened over in the States, and the Buncefield overfill incident in a tank farm in the UK happened both in 2005. Both of them had issues with their level measurement and their trip systems as well, and also there was a number of errors made in the lead up to both those incidents, which I'll talk a little bit about in the first couple of case studies. I then reviewed those incident investigation findings and sort of applied them over quite a few years at the refinery and then a gas plant after that with condensate tanks. And even now, years later, we're still talking about these incidents and what we can apply within design and within the operation environment. The other case studies I mentioned have come from various places. Lots of sort of HAZOPs. Whenever I run a HAZOP or a hazard identification, there might be some level incidents that come, and if I think they're worthy of it, I'll chuck this into this paper to share with others. But yeah, thanks to the numerous colleagues and other workshop teams over the years that helped me identify these issues. Yeah, all the examples related to the oil industry or gas plant type vessels and tanks. So they are really all sort of hazardous chemicals or hazardous materials. So they're flammable and toxic most of the time. But like I say here, the learnings can be applied in any really industry that has liquid level and particularly hazardous fluids and how you keep them within the pipe or within the vessel. So why are we talking about storage levels again, or vessel levels? We just thought earlier this year, I was talking to a few old colleagues, and we heard that, like, people were starting to store their fluids again, or the liquids. Crude oil prices had sort of gone to historically low levels, and they're still pretty low versus last year that was around about $60 per barrel, and they're now around about 40, I think, or just over. They did go down to around 20 during the first wave of pandemic earlier this year. So things like crude, intermediate products, final products, they're all in high, when they're not in high demand, and their demand goes down, the fuel use obviously goes down. People aren't flying so much, people aren't using their vehicles so much, industry's not using so much fuels. So they've had to start stockpiling or storing the intermediate products and the final, and changing sort of the demand on the tankage. So that's one reason why we wanted to start talking or raising the awareness of, because people are filling up their tanks more and filling up their vessels more. The other thing is sort of considering the issues around management of change. It's very important. Bringing back old tanks into service. There's probably a number of old tanks that have been brought back into service over the last year or so, and you're filling them probably to higher levels than you were before, sort of sailing closer to the wind, if you like, in terms of the trip levels or the alarm levels. But every time you bring something back into service, you need to do a proper management of change on it. And so some of those issues, I'll talk about those today. So tank overfill is still happening. The 4 years after Buncefield, there was another incident, and it was called Capeco. So Capeco was an oil storage facility in the Caribbean, and they had a fairly large overflow, and you can see the photo at the bottom here in Puerto Rico. So October 2009. Now, if anyone hasn't heard about this one, then it was very similar to Buncefield that happened 4 years before in the UK. One of the tanks overflowed, caused an explosion, fire and explosion, and as you can see, devastation to all the other tanks in the tank farm nearby. Now, if you want to actually see an animation of this, you can go to the csb.gov website, so the Chemical Safety Bureau or Board in the States. They've got a number of videos that are very worth watching, including the Texas City one as well, but this one was called Filling Blind. So if you look that up, you can get all the details of that one and learn from it. In their case, they had an overflow of around about 200,000 US gallons, which is somewhere around about 760,000 litres. It was detected and the transfer was stopped, but by the time it was stopped, the bund drain valve was left open, so the liquid that had spilled over into the bund there had gone down the drain. It flowed from the bund, it reached the waste treatment plant and ignited by an unrated piece of equipment over in the waste treatment plant. It caused the flame front to burn back to the bund, causing an explosion, and the resulting explosion was around about 2.9 on the Richter scale, so a pretty large bang. Fortunately, no one was killed, but 17 different tanks were destroyed on that facility, and 300 nearby buildings were damaged. So pretty extensive damage on that one. So that was almost exactly the same incident that's happened at Buncefield 4 years before, but unfortunately, there were no fatalities. But in both times, they were sort of lucky in that respect, but very unlucky in terms of ignoring the signals leading up to those events. The US Chemical Safety Board also came up with a number of findings around control failures. So they had unreliable level control and monitoring systems that did not provide accurate and timely information for the operator to prevent filling. Failure-prone float and tape level gauges, unreliable level transmitters proved ineffectual. Frequently out of service due to lightning damage, apparently. They didn't have independent and separate safeguards versus the control measures. So such as the high level and the automatic overfill prevention system weren't independent from each other. They also talked about procedures, they talked about management systems that had failed, and they talked about human factors in terms of the drain bund valve being left open. So basically people weren't learning between those two incidents, and even now people tell me they don't know about this Capeco incident or even Bunsfield, so it's worth reading up on those things and acting on the findings. So we've got our first, we're going to do some poll questions here. So Trish is going to bring up the question for you. The first one here is for operators in particular, so those who work on facilities with some sort of storage. So the first question there, have you experienced a liquid overflow or overflow event of hazardous fluids at your facilities in the last 10 years? So it's effectively it's been 11 years since Capeco, but I'm hoping that people haven't had one, but maybe a few have, so we just thought we'd ask that question to start with.
Okay, Gary, I'm seeing the results come in now, so we've still got results coming in. Give it a little bit longer.
Okay.
So right now we're actually at about a roughly 30-70 split, 30 yes, 70 no.
Okay.
Roughly. So we seem to have stabilised out with the voting numbers, so I'll show you those results now on the screen. So 32% said yes and 68% said no.
Wow. And how many people roughly? Or do we not know that?
No, 71% of the audience voted.
Yeah, but it does show, like, if it's 30-odd% people watching today, and presuming there's quite a few people watching, that's still quite a few overflow events in the last 10 years. Certainly. So hence, I mean, even with the COVID restrictions and filling up, it shows how people are still able to deal with these issues. So we'll carry on. That's a good, insightful answer. The second one here I've got on my screen is for designers or suppliers, so those who are sort of dealing with control systems or measurement upgrades and that sort of stuff for tanks and vessels. So what I've said here, I mean, you might just say yes, but have a think about it. Do you review and suggest improvements to existing liquid level measurement practices and related control safeguarding when upgrading, changing or modifying vessels and tanks? So it's a yes, no, or depends if the client actually asks you for that information.
Okay, so we've got about 43% voting so far, or up to 50% of the audience. We'll just give it a little bit longer till it stabilises. Okay, we seem to have stabilised out with the voting, so I'll close this poll off now and show you the results. So 78% yes, no one said no, but 22% said, well, it depends if the client asks for it.
Yeah, that's it. So the reason I put this one in, I didn't think anyone put no, but it's good that people do consider that, and they do sort of enlighten their clients or the operators who ask for the upgrades. But it depends if the client asks. For me, you shouldn't really be prompted to be giving that information. So if you know of a better way of doing things, it's your sort of duty of care, if you like, to give that information out freely. Yeah, so I'm not sure. I mean, obviously we don't know the background of all these things, but yeah, just changing out like for like all the time isn't necessarily the best thing to do. So, and also just going for the latest technology may not be the best thing to do either. If it's not been tried in the service it's going into, it's probably a sort of risky thing to do. So you have to just think about that, but give the options and work through them. So that was the reason for asking that question. Okay, so we'll carry on. Thanks, Trish. So now I'm going to go a bit more into why level measurement's an issue. So we've already established there's people still having those incidents out there. number of times the incident findings have found poor or faulty level instruments, or the lack of understanding of how they work has been a significant contributing cause, as it says here. Yep, there's various services, not just on refineries, but elsewhere, where they rely on the instruments to work and do the right thing. And sometimes they can be a safety critical task, like they might be preventing a blow-by sort of from a high to low pressure system to prevent overpressure downstream. Obviously for overflow, it would be to stop the hazardous fluids going into the atmosphere and causing flammable or toxic environment. Or it could be that it spills into another system that's not designed for it. And the same in Texas City, it could be that it actually goes into a vent stack that eventually overflows the vent stack. If one system fails, and then the next one isn't ready for it or can't react. So it's often picked up as an issue in HAZOPs, in still assessments and audits, but it may be missed. And one of the things I find in HAZOPs in particular, people just assume that because the level protection is there and there's a trip, that it's going to work every time, or it's good for the service it's in, and they don't necessarily think about the type of conditions that could change that, which I'll explain as I go through. So the other thing I wanted to talk about was just around human factors. So we'll have this normalization of deviance. I know Trish has talked about this many times as well in her presentations. So this is really where people have done things differently over a period of time, a number of times, and nothing's happened bad. You know, nothing bad, no bad things have happened yet. So it sort of gets normalized as the way to do things, even if it is actually an unsafe or a shortcut way of doing things that's maybe easier than the procedure says. But it hasn't been risk assessed, hasn't gone through any sort of management of change. So you can normalize things, and it could end up actually being an incident in the end because you've bypassed or done something that you weren't supposed to be doing. The other thing that's not mentioned here, but things with overflow would be like acceptance of leaks or spills happening over time, and each time they've only been a small volume, they haven't ignited, no one's been hurt, there's been no environmental problem, so it's sort of accepted as the way this is just the way it is around here. You mop it up and get on with it. You don't really investigate the reason why there was the leak or the overflow. So that's again normalization of deviance. The next one down is the inadequate knowledge. So hopefully through this talk you'll realize that level instruments don't always measure exactly liquid level. They look at delta pressures and other things. So if it's not a direct measurement, then it's good to know that, so that when you're analyzing it, you know how it could fail. The confirmation bias, we'll see that a couple of case studies where you're seeing what you're expecting to see. So you make a change, and the change causes the level to go higher or lower, and as a result you see that on the instruments and you just accept it and carry on. Whereas we'll show you on Texas City and other examples that can actually be not a good thing to do. And it's confirmation, it's a bias of confirmation, that you've seen what you wanted to see, and in fact things are going the other way. And the final thing is just having a questioning mindset. So often, particularly late on in hazard studies and things, people get tired, and so you stop questioning and you're just really going through the motions. But it's having that conscious in the back of your mind, you need to be questioning things. And if you are getting a bit tired or fatigued in those, you know, come back a different day, get refreshed, have a break, and then start challenging and asking the right questions. So the other thing to mention, there's all sorts of different ways of measuring level, and I'm only really going to talk about 3 of those things today. So the DP cells are quite common on hydrocarbon facilities and refineries in particular. So pressure transmitters is what they use to measure the level or infer the level from a DP cell. There's also floats and displacers, they're the ones that sort of float up and down. They might be linked to a magnet or something to show you the level outside, or they may be linked to a sort of gauge that can then go onto the DCS or elsewhere in the control system. And the third one I'm going to talk about is radar systems, those that sort of bounce radar waves and are sort of less intrusive, so they're not actually inside the vessel or the tank. They get the level from outside the tank, sort of bouncing that beams in and out. All the other ones, servo, fork switches, ultrasonic magnetic laser, nuclear capacitance, all these things you might have on your facility, or you might be thinking of designing them. I'm not talking about those today, but it's good to know about those so you can look at the alternatives, particularly if issues are happening on the site. You can sort of suggest those and talk about the pros and cons of each. So moving on to the first case study. So Buncefield, 2005. It's very similar to the Pecco incident I talked about earlier. Large gasoline tank overflowed, so petrol, gasoline, formed a vapor cloud and ignited, causing a major explosion. And there was extensive damage, both to the facility and the neighbouring businesses. It happened on the lead up to Christmas, around this sort of just after this time, so it was early December, and caused a lot of business to go out of business, and then there were lots of legal action and other things. It was also the largest peacetime explosion in Europe since the Second World War. Massive explosion, but because it happened so early on a Sunday morning, there was no one really around to get hurt. None of the businesses were in that day, so although cars and damage to buildings was extensive, they were very lucky just for the timing that happened. The sequence of events on this one, as you'll see here, the things in red, talking about level again. So they started filling a tank. They increased the flow shortly before the explosion, but the level gauge was sticking, so there was no change in output and no alarms for a period of time, something like 3 hours before the event happened. There was also an independent high-level switch that should have either told the operator something was going wrong or stopped the flow. In this case, it had been put into a position where it should have had a padlock on, locking it in the right position, but after maintenance, it was locked in the wrong position, which means it would never have worked in at that particular time. The other thing was, for a number of months before, since the last maintenance period, there had been lots of reports of sticking gauges and things, but they were never acted upon. And so over time, they just sort of accepted that this was happening and didn't really go and fix it, and eventually had the incident back in 2005. So as you can see here, there's extensive vapor clouds and ignition, and then the big explosion that we saw on the previous slides. So yeah, if you want more information on that one, if you Google it, you'll find lots of things. And there was a massive investigation happened at the time in the UK, and yeah, I think the published findings were about 2 years later in 2007. So Texas City. So this was a large sort of facility. I think it was a refinery out in Texas City, and it happened a few months before Buncefield in 2005. Now this was a raffinate splitter column. So a liquid overflowed, hot hydrocarbon liquid and vapors released from the vent stack, vapor cloud and ignition. And unfortunately, we weren't so lucky as the other guys. They actually happened during the day, and there was a meeting going on in trailers that were parked fairly close to the incident. You can see them in this picture just behind where they're spraying the water onto the column. And you can also see the vent stack there. That was the one that overfilled, and that's actually where the loss of containment was. But yeah, 15 dead and a lot of people injured, and extensive damage and downtime. And BP more or less went out of business as a result of within the US, particularly after the Gulf of Mexico incident happened a few years later. So again, sequence of events, you'll see the things in red here. It was a startup phase, and that's always sort of one of the most risky phases of any plant. They filled above the 100% range of the instrument. The high level alarm did sound, but the independent high level alarm failed, similar to the Buncefield and Kopeka. Yeah, the bottoms rundown at the time wasn't commissioned, but they started up a reboiler, and then that added additional feed and also started to heat up. And it was the heat up that actually caused some of the measurement issues that I'll show you in a second. The level indication was showing 80 to 90%, and it was slowly coming down. So the operators didn't actually think they were overflowing, even though the level was rising. So yeah, as you see, there's a number of things failed in terms of the level indication, the alarms, and the way the operators reacted as well. And I'll talk a bit more about that now. But yeah, if you look at the CSB website and look up Texas City, there's 2 or 3 different very good animations on this, and they reissued the animations, I think, at the 10th and 15th anniversary, so there's a number of different sort of takes on the same incident, which is worth watching. It actually was. You need to know a little bit about DP cells, or delta pressure cells. They actually infer the level by measuring a pressure difference, not by direct level of measurement of the liquid. So in this case, the delta pressure is proportional to this rho GH, where rho is the density of the liquid, G is the acceleration due to gravity, which doesn't change, it's constant, and the height of the liquid column, or the height of liquid within the tank or the vessel in meters, is the H. So just very approximations for that particular example at Texas City, if water's an SG of 1 or 10 kilopascals, then raffinate feed, which was the feed they were putting into the vessel at the time, ambient temperature would be around 7 or 0.7 SG, so it's less dense than water. The raffinate feed, if it was heated up though, would become less dense and go to about 0.6. The heavy raffinate, which was normally in the bottom of the column when it's operating, and that the level measurement is calibrated to, ambient temperature is about 0.8 and at 200, 0.7. So you can see there's actually a difference now already between the way they calibrated and what they were actually feeding into the column at the time. So what this means is, here we show the DP cell on the right hand side here, and just bring my cursor over. So over here, you can see that because of the SG difference between the bottoms that's normally there and the feed that was being fed up to the middle of the column, the outputs would never read more than about 87.5% of the output of the level instrument, rather than 100%, because of the SG difference between the two different liquids. So that was straight away before they even started, they had a problem. So even if it's 100%, it would only showing them 87.5. So the other thing is that it needs to be calibrated for the temperature. So if it's calibrated for colder fluid, the density will be higher, and if it's hotter, the density will be less, and so there'll be an error there as well. So at Texas City, as the tower heated up during the startup process, the level appeared to come down, although it was actually above 100%. So the operators were looking for a reduction in level, and they actually got that in terms of their level instrument, but they didn't look for a second measure, if they could, further up the column to see if it was still rising. And there were other trips and alarms failed anyway. But they got this confirmation bias that the level was reducing, and it was actually the heating up of the material that was causing the level to decrease on the measurement. Okay, so going to move on to the next poll question. So this was just, I've mentioned, Buncefield, Texas City, both in 2005, and then Capeco at the start, which was the Caribbean petroleum incident 2009. I just wondered if people have heard about these. Sort of yes, no answer.
Okay, here's the poll.
Yeah, I can see it. Yeah.
Yep. All right. So I've got answers coming in. I'll let you know when we've got a stabilized response rate.
Cool. So while we're waiting for that, just for those who have said no or not quite sure, or about one or two of them, I've written down on my slide when it comes back just a few places you can look for more information, but we'll show that up in a minute.
All right, I'm going to close off this poll now because we've got 82% have voted in it, and it's a fairly stable number. So if I share these results with you, 79% said yes, but there's 21% of people who have certainly learnt about a particular event today. So I think that's a fantastic outcome as well, Garry.
That's good. Good, yeah. So 1 in 5 have learned something today. And hopefully it's reminded those, because if you don't look at these things for a number of years, you forget some of the golden nuggets of information. So it's worth refreshing people's memories if they haven't seen them. So thanks for that, Trish.
No worries.
Yeah, so on this slide here, there's a few places you can go for more information. So there's the Filling Blind Anatomy of Disaster, which is Texas City and Capeco incidents on CSB's videos. You can ask Trish in the ISC about their tank farm case study, which is a good one for hindsight bias in terms of how you could come up with the same incident again by following through the same sort of decision processes as they would have done in an incident. And then the last one, there's the Bunzville incident findings, which you can Google, and there's extensive literature on that. Okay, so we'll keep moving. So now we're going to talk a little bit about installation. So in terms of level measurement, you can do it directly in the actually in the vessel. Then you can have other issues, as I'll mention. You can have through the wall measurement, which is typically done as we've shown on this photo here. You can see stabbings to the side of the tank or the vessel there, and then you either have a direct measurement of level, but it's outside the vessel, or you have an inferred level through DP. So yeah, the connections are usually directly on the vessel, or they're inferred. So yeah, bridles and other things I'll talk about now. The other thing you can have is within the tank, you can have a standpipe, and that's just to prevent things like foam and sort of movements within the vessel causing the level to sort of give you the wrong measurement. So this, some of my friends down in Victoria, Port Campbell, might recognise this vessel because they gave me the photo to use. But this was just to show you what happens if you've got a bridle on the outside of the vessel, and then you've got an insulated vessel that might be at a different temperature. So what I've said here is what happens in a hot service if the vessel is insulated but the bridle is not. So I'm not looking at a pole here, so I'll just give you the answer. So different densities, so you're going to have different densities. The liquid in the drum will be hotter, and thus it will be a lower density than the colder external level bridle. So if you forget to insulate the bridle as well as the vessel, you'll end up with different temperatures. And so there'll be a higher level in the drum because there's sort of the density is lower, and so there's more sort of liquid volume, if you like, and level there, versus the outside bridle. So it'll actually give you a lower level measurement than you've got in the vessel. The other question I had is around independence. So in this case, you can see there's a level gauge, and there's the level bridle, and then you've got a level transmitter on the side of it. And what you might have also is a trip that's off the side of this. So if the independent high or low level trips attach to the same bridle, is it really truly independent? Now, in HAZOPs, I've seen people say, well, I've got one of each, so it's independent, no problem. Two different transmitters one going to a safety logic, the other or safety transmitters, and the other one's going to a control system. So they're independent, but actually they're not, because if you get any sort of blockage in any of those common connections to the vessel, you'll also get common failure. So common cause failure you need to think about. And as I mentioned before, you also need to think about will you lose control and the stripping action or the safeguards at the same time as the incident's occurring. Okay, so going on to another case study. So this one's a gasoline-like material called alkylate in the bottom of an HF acid unit. So they've got a bridle on the side here, and over time the nozzles would block up due to iron fluoride deposits plugging the nozzles. So what happens if the nozzles plug up? So the question here is, if the bottom nozzle blocks up, most people would say, oh, I'll get a low indication, they're not really sure. But in this particular case, you get high level indication because the bottom nozzle will block up, and the vapor that's in this top, because you've got liquid at the bottom, is the liquid level, and you've got vapor at the top of the vessel. So the vapor would start condensing in the top leg and actually cause this bridle to fill up, and so the liquid level indicated on the level transmitter will be high. So now if the bottom nozzle is okay and the top nozzle starts blocking up, or someone shuts the valve by mistake, you'd actually again get high level indication. Now the reason for this is because the vapor that's in the top leg starts condensing, and as it condenses it causes a vacuum and actually sucks liquid back up the leg. So you get high liquid level again. So in either case you get high liquid level. Now that's not something that's that intuitive, you have to think through that. You may even have to find out from your own facility whether that's possible. But yeah, certainly if you get condensation, then you can get this vacuum effect, or you can get liquid, sort of extra liquid going into the top leg you wouldn't expect. So what did they do to solve it? In this case, they had high and low level switches on this bridle and the control system with high and low level alarms. So the controller operated with increase the bottom's flow rate, and unfortunately, by trying to bring the level down, even though it was actually probably lower than it needed to be, it was measuring high because of the blockages. It'd actually end up getting a low level alarm, and sometimes the level alarms or the trips would fail, and you get cavitation of the pump that's coming out the bottom because you've lost the level and the liquid flow to the pump. So that's what was happening. So they decided, let's put a second level control system in. In this case, they put this in, but both sides had the same technology, and so blockages occurred, and they had the same issue on both sides. So even though they got independence, they had the same issues. So they had to start doing daily flushing and rodding out of these different things. So you could put an automatic rodding system in, but they were finding that they had the same problem. So it doesn't always solve the problem by just putting the same thing on either side. Yeah, so over time, they stopped doing the rodding, the flushing, and they got back to the same instance they had before where they were having the pump cavitating. So it didn't actually fix the problem. So they need to investigate a bit further. Okay, this one, a boiling liquid now. Now this is just to show that with boiling liquids, it's quite hard to work out what the level's doing sometimes, because in this case, they've got a stab-in reboiler boiling up the liquid. And so they'll have some sort of bubbling up going on and vaporization further up. And so again, they've measured between the liquid level and the vapor, but what they've done is put an internal baffle in, and then they can infer the level is sort of an average level is within that baffle area, which isn't quite as infected as the main process flow or the process within the vessel. So this is an inferred level. Okay, so the other thing you can do is you can don't measure the level as such, and you can look at the DP between the pump suction and the bottom tray. That's another way of doing it. Okay, coming on to another example. This one, not the original design, but they had a SIL or a safety integrity level rated low level trip. Prevent pump damage, you've got to pump down the bottom here on the drawing. This was to stop cavitation of the pump if they lost the level. But what they were finding is at high flow rates, there was a big pressure drop along this pipe here, which was only 3 inch. Quite a small line, quite a long line as well, 12 meters before it got to the pump. So it's pretty, well, I don't know, I can't comment too much on the design, but you'd expect them to put a bigger pipe there probably to solve that one. But the operators had disabled the trip because it was causing them so many spurious low-level trips, even though there wasn't a low level there. It's just due to the DP, and because it's measuring delta pressure between the vapor and the suction of the pump, it was causing the trips to occur. Okay, next one. But now we're looking at batch systems. So this batch reactor, it's got a vessel here with a stirrer in it or mixer, and it's got a float type transmitter in it and a stilling well with the transmitter at the top there. So it's initially filled with one chemical, say density A, and then it's topped up with several other chemicals before they start the mixing and the reaction process. So while they're doing the mixing, the volume and the temperature changes, and while the reaction's going on, same thing. So originally they had a float arrangement, but it was sticking. So they proposed, the vendor proposed a guided weight radar. So they're using radar to sort of measure the level, and that would mean that it's non-intrusive, it's not within the vessel anymore, so it should be more accurate, I think, than a float type. So the plant engineer, he sort of expected the project engineer and the vendor to simply replace the float with this and the stilling well, so to take out this arrangement and just put in a radar within the vessel. So what he actually got was quite different, and that can occur if you don't look closely at what the vendor's going to give you or ask them. So what they wanted was, as it shows here, this type of swing. What they actually got was something quite different. Yeah, what they actually got was a guided wave radar, but it had been put into a bridle bypass line, if you like, on the outside of the vessel rather than within the vessel. So the problem then they had was blockages, top and bottom, like we said before, condensation, and all these other things happening that could cause the level to give them spurious readings. So it's not direct level, and as we said, temperature and density changes, and they can get the condensation going on as well. Okay, so coming on to the last couple of case studies, and then I'll finish up. So this one was a acid, again back to HF alkylation unit, an acid dump system. This was basically a waste system, if you like, or a flare type system where it dumps the contents, and it mixes various things in this drum, and then some of the gases and things are then flared via a caustic scrubber just to clean them up. So what they had here was a standby pipe again and a float on the side of it, float level measurement. Now it was sized, the drum was sized for the full inventory of the reactor, so it could take everything, it could all come through, and it was a mixture of alkylate and unreacted butane, so about 40 tons, and it took about up to about 10 minutes to fill up. But there were two problems with the system. It's basically three-phase. They had liquid, they had a foam layer, and then they had gas. And there was no way to directly measure the hydrocarbon phase in the drum with just one measurement. So they got an indicated level, which was actually different to what the level actually was because of the foam layer that was in there. So what they really had was foam, then a hydrocarbon layer, and then they had the acid underneath that as well. So they had sort of three different layers or levels they were interested in, and they couldn't do that with one instrument device. So it's really to say, if you've got this type of thing going on, then you need to look at maybe multiple stabbings at different levels within the vessel, different alarm settings, and different transmitters, and even different safeguards. You need lots of different things to make sure you measure everything correctly. Okay, final case studies on tank. So this one in refineries, import and export duty, sort of changing the tanks from intermediate or feed service to sort of an import-export type arrangement. Sometimes tanks are being decommissioned, and when they're brought back, they're brought into a different service. So this can happen if the rates are reduced, like they might have done this year, and they start stockpiling feeds or products. For floating roof tanks, though, in particular, when the roof is landed, that's actually one of the major risks. You land the roof and you start getting various failures going on within the vessel or at different seals and other places on the tank. Now, the other thing is the risk of a flammable mixture forming underneath the landed roof. And also when you're swapping out products, you might have air in the line, which will then push into the tank. So you need to think carefully about how you mitigate against that to stop explosions happening within the tank. So there's a direct increase in risk of emptying the tank more often and landing the roof. So in a refinery, maybe landed every 5 to 10 years for maintenance. So most of the time you've got a liquid level in there. Whereas in terminal operation or this sort of start-stop operation with different products, the roof might be landed several times a year, mainly because the customers want all their products back if you're storing it for them. Or if you're changing products, you might be doing it more often. So as we said, there's potential failures, wall-to-floor welds, and also the air getting into the vapor space can also be an issue. So the frequency can, in this particular example, if you're landing it several times a year versus once every 5 to 10 years, the increase in risk is a factor around about 50, so 10 to 50 times more. And so you need to just look at your management change in the risk and what's going on there. Maybe you can accept that risk. So just to wrap up, a few things that we've mentioned. So in HazOps, we're identifying causes of hazardous events. So they're normally either an equipment failure of some sort or control failure, or a human failure of some sort as well. And that could be due to lack of knowledge or just under pressure and do the wrong thing at the time. But level problems can be both, and I think I've mentioned that as I've talked through today. We need to make sure that the level instruments we are relying on for control and safeguards actually work and they're independent to each other. So if one fails, the other one doesn't fail as well. So that's the importance of getting someone in the room in the HAZOP or the hazard study from operations, or a process engineer who has looked through all the instrument logs and found out, what's the chances of actually going to a high level, or how often has it occurred in the past, and whether there's any particular issue outside in the field that you need to talk about during those studies. The final point there is on, don't expect the instrument engineer, vendor, or process design engineer to actually understand how the level instruments works in your situation. So they might know in a clean service or in a sort of a service where you've just got one type of fluid that's going to go in there and no foaming or condensation or any of those sort of issues going on. But often you find, particularly in design HAZOPs, no one in the team really knows how it's going to react within your particular situation. So you need to have a period of time for the first 3 to 6 months, sort of checking back to make sure it's actually giving you what you want, and making tweaks if you need to. Same in SIL assessments. We've said that nozzle, you assume that you've got level, alarm, trip, and they're all sort of working and regularly tested so that they will work when you require them. But just because you've got a SIL rated instrument doesn't mean that the wet end to wet end, the whole control loop, actually meets the SIL requirement. So you also need to think, particularly when it's been operating for a number of years, about things like nozzles plugging up and isolated, whether standby or bridle might give you differences, whether you need rodding and flushing just to keep things working, and whether the process conditions can give you the wrong level measurement. So just to sum up now, before we get to the questions. So I think I mentioned already, failure of level instruments cause many incidents. So we mentioned the 3 big ones at the start, but yeah, there's a number of different examples I've given you there in practice where things have gone wrong, and they don't always intuitively give you the answer you're expecting. Obviously, be aware of your own failures or human factors. So normalizing things, if they've not given you anything bad yet, doesn't mean they won't. And so just because things are giving you the right sort of short-term answer, long-term it might not be the right thing to be doing. Yeah, make sure you know what technology you've got. Make sure that most level instruments don't actually measure level and sort of what indications you need to be looking for. Perform your management of change on your tanks if you're changing the service. Look how often you're opening them and filling them, and don't assume that design is correct, because sometimes it's not. So that challenging mindset you need all the time. Okay, so I don't want to go too much more because we're going to run out of time otherwise for questions. So I'll probably stop at that point and move on to questions.
Thanks, Garry.
Thanks, Trish.
Really interesting points that you've made there, and it goes to show that whilst we often think tanks are a very simple process, they can actually be quite complex. I especially liked your focus in on flooding roof tanks and the issues with grounding the roofs and those sorts of things. That was something I learned very early in my career working in a tank farm. Okay, we do have a couple of questions in here for you. So the first one is regarding Buncefield. So the failure of the level gauge and the failure of the independent high-level switch, they both happened at the same time. Assume it's not double jeopardy issues. Do you want to say anything about that particular issue? I mean, we did see 2 independent systems fail there at the same time.
Yeah. Well, yeah, we talk about this as start HAZOPs quite often. The double jeopardy doesn't mean that between periods of maintenance, something might either fail and not be picked up, or it might have been locked out for some reason and not put back, so shelved or put into some sort of position that means it won't work when required. And that's not picked up until the next time you have an incident, really, unless you've done some testing in between. So in that case, it's not double jeopardy, because in Buncefield example, I think they locked out the level trip. And so the fact the alarm didn't work was yes, it was independent, but it was only one failure, really. Yes, they had the failure of filling too high, but once they'd had the failure on the alarm, nothing else was going to stop it. It was going to go over the top at that point. So that's why I think it's not double jeopardy in that particular case.
Okay, thank you. Any possibility that missing a vortex breaker at the bottom of a vessel disturbed the reading of the level measurement? Any incident experience related to this case?
Yes, I've had vortex breakers where the flap of metal or whatever that goes across has broken away, and so you do actually get the vortex, and that does cause level measurements to fail. And particularly if you've got something pointing in the right, like radar or something pointing to the wrong place within the vessel, then you can have lower levels and different because of the vortex. And also it can sort of vortex towards the side of the vessel, and then you're reading a level from a bridle that's nearby, and it will give you the wrong result. So yeah, I've seen that.
So I guess it's important then to make sure that you've actually got proper flow modelling of what's going on inside your vessel at that point in time.
Yeah, true.
Yeah, to understand where that impact could be, and then look at how you can resolve the level transmit issues. Okay. If we have a foamy liquid, what is the best type of measurement to be used?
Well, you can use, I mean, I showed you one with DP cells, and it just depends what you're using on site. But the main thing with foam is that there's probably 2 or 3 different levels you're interested in, and sort of the foam will be probably the thing on the top. So if it's a stabilized foam, then you probably can't see the foam itself because it's probably a lot less dense than the actual liquids. So then you'd need to make sure that the top level of whichever this top liquid is, so say it was hydrocarbon on top of water or on top of an acid, then you'd be measuring that and making sure it's well below the top nozzle so that the foam doesn't get up there. I've even seen some places where the foam sort of almost solidifies immediately as it goes over the top, and then it blocks your overflow line or your vent line, and then you're getting overpressures as well as overfill. So it's very important to try and keep those levels down well within the vessel and make sure you sort of oversize the vessel accordingly.
Yep. Okay.
Yeah.
I guess a little bit of a related question. So what do you think is the best level measurement instrument for measuring multi-phase liquid in a tank or vessel?
Okay. Again, it's hard to say what the best is. It depends on the situation. But it's just to have enough measurements within that vessel, and it might be multiple instruments you need again. I don't really know which type would be the best. Yeah.
Okay. I guess a question from me, and you mentioned that, one of the things that I talk about is the normalization of deviance and biases are also an area that I'm particularly interested in. And the confirmation bias. So from an operational perspective, what do you think the confirmation bias, the best way to try and overcome that is in an operational situation in your experience that you've seen?
Okay. So my experience probably is just to, if you're relying on sort of one instrument and you're looking for a certain sort of reaction. So in this case, talking about level. So if in Texas City, it went down when it was actually going up. So they were expecting to see it come down, and it did, but it was for a different reason. It wasn't actually the level reducing, it was the density changing. So you'd probably be looking for some other measurement within the vessel or some other confirmation for what you're experiencing. It's hard though, because in that startup situation, it's high pressure, and so they're under a lot of scrutiny, or they've got short time to do things because they're moving from one thing to another. So whether they'd actually do that in that case, so you might actually need someone else, like a unit process engineer or someone else on hand to be watching all those things and looking for confirmation that what they're actually seeing is correct. I did that when I was on the refinery. We'd always have an extra pair of eyes helping the control room operator, and even sometimes they'd have 2 operators looking at the panels, looking at 2 different things going on at the same time. So it's probably just an extra pair of eyes would really help in that situation, not always relying on one person to get it right.
Okay, great. Thank you.
Yeah.
I've got one comment here and then what looks to be one last question. So first of all, great presentation. Thanks, Garry. Just to note, having insulation on external bridle does not necessarily guarantee similar temperatures within the main insulated tank, since there is no flow and we rely on conduction via the upper and lower nozzle. And this is important to consider. If there is a change in process temperature in the main tank, there will be a delay. So it's just a comment.
Yeah, that's fine. Yeah, I agree.
And the last question that we'll do, because we are sort of heading towards the end of our allotted time, can you briefly describe how the level transmitter show high level in the tank if the top leg is blocked? So,
okay. So in that case, the one I was talking about that caused high level by blocking the top nozzle was to do with condensation. So the condensation caused a vacuum. So you had vapor in there. It was actually in a tank. It might be completely different because normally tanks are atmospheric temperature. So you may not get that condensation going on. But if you have got some vapor there and it condenses, then it causes a vacuum that sort of sucks the liquid back up from the bottom nozzle, and that's what causes it show higher level than you would have in the tank.
Okay, great.
Yep.
Well, thank you for that,
Okay.
Garry. That's all the questions we've got, and a couple of comments have come in to thank you for the presentation. So it's certainly been
Great.
well received. This presentation
Excellent.
will be or has been recorded, and it will be available shortly on our YouTube channel. So if you could just flick to that final slide for me, please, Garry, to show the IChemE Safety Centre social media channels. So please follow us on social media. We will be coming out with some more webinars over the next period of time. So check out what we've got to say on those things. We will have a lot more different activities and webinars for you to attend and continue learning. So if you want to contact Garry directly, his email was on that previous slide, so please feel free to if you'd like to talk to him about anything to do with the levels. But otherwise, this video will be up on our YouTube channel later today. So Garry, thank you very much for taking the time to take us through this presentation. Greatly appreciated. And I think our audience very much, certainly judging by the messages I'm getting, thank you for that. So I'd like to wish everybody a very safe day. Thanks.
Yeah, goodbye, everyone.
Bye.